Welcome back, ladies and gentlemen. This should be the most difficult topic in the stoichiometry unit. Not necessarily the most complex, but it just has so many steps and it's so easy to get lost, especially because this limiting reactance builds on everything we've done up until this point, which means if you're not clear on the previous steps, this is going to get tricky. You're effectively, well, to use an analogy from physics class, you are effectively building a bridge across the river at the same time that you're walking across that bridge. If you're not very stable up until this point, you might end up falling in the river. Now, on the plus side, I'm here, and I will help you to get out of the water if that happens. So, let's start off by taking a look at limiting reactants. So it says here, up until now, we've assumed that they have an unlimited amount of most reactants, which is reasonable in many cases. Right? So if I, for example, want to burn some paper, I can say there's an unlimited amount of oxygen in the air. Right? So for example, I can take the very page that we are using for our notes. If I wanted to burn this, I could just be like, light it on fire, and it burns. And what's going to run out first, the oxygen in the air or the paper that I'm holding? Well, this is one piece of paper. The air is, of course, a lot. It's a big room, plus there are vents that bring more air in, all sorts of stuff like that. So realistically, this will run out before the air does. Now, sometimes there is a limited amount of all reactants. Like, for example, if I tried to burn the paper while trapped in an airtight box, now I don't get infinite air, I get a limited amount. Usually one reactant will run out first. The question is just which one, and we call that one the limiting reactant or limiting reagent, and it means the same thing. Now, this name comes from the fact that the reactant will limit for how long the reaction can occur, or it will limit the amount of product that can be generated. Once you run out of the limiting reactant, everything stops. So the material that we have left over we call the excess reactant because it's unnecessary, it's extra. Now, this is all fine and dandy, but it's pretty nebulous, it's pretty abstract. We're going to go with something a little bit more concrete. Let's say you're trying to make a ham and cheese sandwich. You have 5 pieces of cheese, 6 pieces of bread, oop, I know what 6 is, and 12 12 extra digits, I got nothing, and 12 pieces of ham. How many sandwiches can you make, and will anything be left over? So we have, as written on the page here, a sandwich equation. Sandwich equation, of course, in this context is 2 pieces of bread plus 1 cheese plus 3 ham equals our sandwich. Specifically, 1 sandwich. Now, in this context, with the numbers that we have, right, how many can we make? All right, let's remind ourselves what the numbers are. So we're going to have, I think it said, what numbers did I choose? We said 12 pieces of ham. We said 5 pieces of cheese. And we said 10 pieces of bread, 6 pieces of bread. That's almost like 10. So what's going to run out first in this context? One of them will run out first, but which one? Well, one of the ways that we could try to solve this is that we could just simply work out how many sandwiches can we make with each of the different ingredients. So, for example, I have 6 bread. That is almost an A. There we go. 6 bread. I want to make 1 sandwich. Conversion matrix. See, look, I can use a conversion matrix for anything, including making sandwiches. Admittedly, these are chemistry sandwiches, so that makes sense, but anything. So I want to get rid of the bread, and I want to get the sandwiches. And the connection between the two is that for every 2 of these, you get 1 of those. So what do we get? We can get, not 1 sandwich, 3 sandwiches. Okay, that makes sense. I mean, obviously I didn't really need the conversion matrix, but there's a reason I'm doing this. You'll see in a second. Then we've got our cheese. Well, same thing. 5 of the cheese, brackets. We're going to do 1 cheese for every 1 sandwich. So we're going to get 5 sandwiches. Finally, the ham. We've got 12 ham, bracket. We're going to do 3 ham for every 1 sandwich. And that's going to give us a good old 4 sandwiches. Okay, so we figured out how many sandwiches we can make given each of these different reagents or starting reactants. But how many sandwiches do we actually make? Well, which one runs out first? The bread does. Once the bread runs out, I can't keep making sandwiches. I mean, I can keep putting ham and cheese together, but it's not a sandwich without the bread. Well, that's not totally true. Some people do those lattice wraps, and then there's at least one fast food restaurant that'll do like a sandwich that's just meat wrapped in other meat. Well, for our purposes, in order to make this chemistry sandwich, you need the bread, and we don't have it after we make 3. So that's it. We see that the bread here is the limiting reactant because it runs out first. In a lot of ways, what we've done here is we've sort of calculated some theoretical yields. These two are, of course, in excess. Which one is more in excess? Well, this one is more because, well, why because? Let's take a look. Meat and cheese are both in excess. Note, there is enough cheese for how many more sandwiches? Well, let's see. We had 5 pieces of cheese. We make 3 sandwiches, and then we have to stop. So how many pieces of cheese do we use up? Well, we used up 3. So 5 minus 3 is 2. So we have enough cheese left over for 2 more sandwiches, but we only have meat enough for 1 more sandwich. Why? Well, we started with 12, but we made 3 sandwiches. 3 times 3, right down here, is 9. 9 from 12, that's enough for 1 more sandwich. So we have enough for 1 more sandwich, but we have enough for 2 more sandwiches of the cheese. So that means that of these two, cheese is the most in excess, and the meat is close to being a limiting reagent of its own, right? If I brought more bread, somebody showed up and they said, here's more bread, Mr. C, I could only make 1 more sandwich before I ran out of meat. So that's the basic idea. And now we're going to take that basic idea and we're going to apply it to chemistry. Take a look at the next page. When trying to determine the limiting reactant, you first need to work out the balanced equation. And then remember, the limiting reactant is about which reactant runs out first. So the example we're going to work with here is we're going to burn 2 moles of propane and 7 moles of oxygen gas according to the reaction listed below. Let's get a little space on the board. But keep this in mind, because this and how we did this is going to be very important. So our balanced reaction is going to be with propane, which I think is that, no, not a P. Oh, Mr. C, it's propane, yes, but it's with a C. And then we've got, some oxygen gas is going to make some carbon dioxide plus some water. And it tells us that we're going to have 2 moles of propane and 7 moles of oxygen. So we're going to have 2 moles of this and 7 moles of that. And the question further then says, how many moles of carbon dioxide do we make? Okay, so I want to know that. Well, step 1 is always balance the chemical equation. We got 3 carbons here, so this is going to be a 3. 3 times 2 is 6. Oh, but we got another one there. But we've got 8 hydrogens. Let's get the hydrogens balanced. So we're going to put a 4. 4 times 2 is 8. So now in total for oxygens, we're going to have 6 here, and we're going to have 4 there. So that makes 10, so this is going to be a 5 in front. All right, good. Whew. I was worried it was going to be a hard one. says Mr. C, as people in the audience are going, ugh, balancing. It's been a while. All right, so there we go. We've got ourselves a balanced chemical equation. Now what do we do? Well, think about what we did with the sandwich. We then worked out how many sandwiches we could make with each of the different reagents, with each of the different reactants, right? With the bread, with the cheese, and with the meat. So let's do the same thing. We have 2 moles of propane. How many moles of carbon dioxide can we make with that? All right, let's give it a try. 2 moles of C3H8, and I want moles of CO2 equals. Okay, the balanced chemical equation is how we're going to do this with stoichiometry, and we're going to see that there's 1 of these for every 3 of those. So this is going to be times 3, that's going to be 6. So we have 6 moles when we're finished. All right, so we now know how many moles we could make of this product with this starting reaction. Now let's try the O2. With the O2, we've got 7 moles, so we've got more of O2, but we're trying to make moles of CO2 still. Oh, and I chose CO2 because the question asked for it. If the question asked for water, I could do that. If the question asked for nothing, I could choose whichever one I want. So down here, we're going to have moles of O2, and we know that one's a 5, and this one's a 3. So even though this is a much bigger number, this ratio is a lot steeper. So it might not work out so well. We get out our trusty calculator, we calculate it out, and we get 4.2 moles of CO2. So now remember what we did with the sandwich. The one that ran out first was what actually happens, because obviously I can't keep making more if I run out too early. So this must be the limiting reactant. This must be the excess reactant. So the question says, how many moles of carbon dioxide are formed? 4.2. That's it. We're done. All this requires is that we have the ability to compare 2 possibilities and choose the one that makes the most sense. When will the reaction stop? When one of these runs out. Which one is going to run out first? Whichever one makes less. Because that's how logic is, right? If I make less, I run out earlier. All right. That's for part A. There's a part B. Oh no, what are we going to do? Part B, what volume of carbon dioxide? Wait a second. Volume? That's just a conversion. I've got moles. I just need to turn it into volume. Well, that's not so bad. I mean, we've done that a lot. So I just take my volume. Let's do it with green. Sure. We're going to do like so. I want to get liters of CO2. So I put in 1 mole is equal to, let's see if you guys remember the number. I've written it. Can you guess what it was? Do you remember? I hope you do, because there it is, 22.414. Often people drop the 1/4 at the end, but whatever. I'm being particular today. You multiply that out, and you're going to get 94.14 liters. 94.14 liters. So there you go. How many moles did we make? This many. How many liters did we make? That many. This is very much like any other stoichiometry question. You're just bolting new pieces onto an existing framework. Previously, we started off with just doing this, mole to mole. That was stoichiometry level 1. Then we said, okay, good, you know level 1. Now I want you to do some conversions with it. So then we added conversions at the end and at the beginning. I could have given you these numbers not with moles, but with grams. Then you would have had to convert them. In this case, you didn't, because this is the first example. Let's not go too crazy here. But I could have made it so you had to do another step. But it's not a hard step. And really, the only part that we've added that's new is that we do 2 calculations, and we see which one runs out first. A theoretical yield, as it were. Okay, so that seems to be it. That doesn't seem so bad. Oh, okay, there is one more step. Remember with the sandwiches, and I asked you how much cheese do we have left? How much meat do we have left? How did we do that? We took the amount that we started with, and we subtracted the amount we used to get what was left. We got to do that with chemistry too. Because, again, your boss might call you up and be like, hey, incredibly smart chemist that I pay lots of money. We can dream. Incredibly smart chemist, I pay lots of money. How much of that excess reactant you got left over? Can I sell it on the side, or maybe bring in another shipment of the original limiting reagents so we can do this again? You got to be able to tell them. Not to mention, it tells you how much you got to store away for later. So if you flip over the page and take a look, it tells you here, sometimes the question will go a bit further and ask how much excess reactant remains after the reaction is finished. This is like the sandwich example asking how much cheese was left. And the way we do this is by doing a bit of subtraction. Now, the tricky part here is, where are we going to subtract? Do we want to subtract early or late? Both will get us the right answer. The question is just how much work we have to do. Now, that said, we need a little more board space, and what we've got over here, we don't really need. Not anymore. That was the answer for part A, but part B is a different beast entirely. That said, I probably don't actually need to erase it, because what we're going to do isn't going to take that much room. We have calculated two possible products, how much we actually made and how much we could have made. To figure out the excess, what I want to do is find the difference between these two. What's the gap between these two possibilities? So to do that, I'm going to take 6 moles that could have been made and subtract the 4.2 moles that we did make. So we'll take the 6 minus 4.2, take that, plug it into our trusty calculator, and end up getting 1.8 moles of CO2 not made. Now, that doesn't seem useful by itself. We didn't make 1.8 moles of CO2, but remember, we didn't make those 1.8 moles of CO2 because we ran out of oxygen. So now I'm going to do just a tiny little bit of stoichiometry. I'm going to transform the moles of CO2 that we didn't make into my excess reactant. So I want to turn this into my C3H8. By doing that, we're going to get 1 over 3. We plug that in to our trusty calculator, and we get 0.6 moles of C3H8 not used. Right? Because we didn't make this stuff, so we didn't use this stuff. And if we didn't use it, well, that's another way of saying that it remains. It's excess. So that means that we've got 0.6 moles of C3H8 not used or remaining. Now, often these questions are going to ask you to turn it into something a little bit more complicated, maybe into grams. We can do that, right? That's pretty straightforward. We just have to do a simple conversion. We're going to take our 0.6 moles and we're going to turn that into grams. Now, can I squeeze it in there? Maybe. We're going to do one last conversion. Let's do it in a different color. Let's go blue, orange. We squeeze it right in the back here. So this is going to be 1 mole on the bottom, and we're going to need our molar mass of C3H8. Quickly throw that together and get 44.11. So we throw that in, 44.11 grams, 0.6 times 44.11, and that's going to be equal to, we got really no room there, so we'll just squeeze it underneath, 26.46 grams remaining. Look at that. Remaining. Now, the process here, again, to iterate, you don't always need to do all of these steps. There are a lot of steps in a limiting reactant question, but you don't always have to do all of them. If the question gave you moles at the beginning, you don't have to convert them into grams. If the question doesn't ask you to find the excess reactant left over, you don't have to do that part at all. If the question doesn't ask you to find the amount of liters of product that was created, you didn't need to do that step. There are a lot of possible steps here, but you don't need to do all of them. You only need to do the ones they ask for. But the key thing to see here, when it comes to the actual limiting reactant question, what is the key thing? We followed two different paths to see which one produced the less amount. The one that produced less is what we continued when it came to trying to figure out the amount of product. The one that produced more, we used to figure out how much excess was left over. We found the difference between the two different extremes, the difference between these two. We converted that back into excess reactant, and that gave us our product or reactant not used. And then finally, we could convert that into grams if we really, really needed to. And that's kind of it. That is the basics of limiting reactants. You'll notice that this basically uses absolutely everything that was in this course. There's not one part of this that we didn't have from some other part of this unit. And so in a lot of ways, this is sort of a culmination, a final test of everything that you've learned in stoichiometry. But again, remember, just because it can involve all these steps doesn't mean it has to. In this question, you were given moles. You didn't need to convert. In this question, they asked you for volume, so you did need to convert later on. And they asked you to find the excess reactant remaining, which means we had to do an extra step there. On top of that, we need to do a balanced equation. So how much work you have to do depends on the context. It's not always all of it. Make sure you know what you're looking at. And I'll leave it there and see you guys next time.